Hi there and welcome back. Now we'll be doing some more simple problems regarding these electric circuits so that we can be familiar with it and somehow we can build our ease for this. Okay, so uh, in this circuit you can see that we have active elements and we have passive elements, right? So um, those active elements they are the ones that producing power, whereas those passive elements they're the ones consuming the power. And therefore we can, one way to check is um, through this conservation of energy principle, that the power produced must be equal to the power cons- power consumed, right? So it says here that one method of checking calculations involving interconnected circuit elements is to see that the total power delivered equals the total power absorbed. So that's the conservation of energy principle. So with this thought in mind, check the interconnection in the figure and state whether it satisfies this power check. The current and voltage values for each element are given in the table. Right, so we have these labels A, B, C, D, E, up to G. So we have these elements right here up to G, and the voltage is given, and the ampere is also given. So we have negative signs in some elements, and we also have these directions. So we need to keep track on this of these assigned directions. So of course, based on the passive sign convention. Right, so what we're going to do here is that we actually don't know yet the actual type of element, whether this one is active or negative, but based on the convention, passive sign convention, we can arbitrarily specify that let's say this is an active element, and we are going to check that later based on our computations, right? So first is letter A. So for letter A, you see that this, right, so we have the current that enters the negative, right? Positive current enters the negative. That's gonna be active, right? So if it's active, that should be negative, right? Active elements means that the power will be negative. Okay, what else? So for letter B, based on the passive sign convention, this positive current enters the negative terminal, and this is also active. So this is negative. Okay, next one is letter C. So letter C, the positive current enters the positive terminal, voltage terminal, so that's gonna be passive, and this one will be positive. Okay, next one is letter D. So letter D, this is active element, so active. And for letter E, this positive current enters the negative terminal, and this is also active. Next one is for letter F. So the letter F, although in this direction going downward, but it enters the negative terminal, and therefore this is active based on the passive sign convention. And lastly, for letter G, element G, this current enters the positive terminal, and therefore this is passive. Right, so now if we check the voltage, we have this P is equal to VI. That's just voltage times the current, and we have this positive and negative. So anything that's positive, we are going to write it here, right? And anything that's negative, we are going to write it in this negative column. Right, and just take note, since we have this given value, positive or negative values, then we have to multiply this. Let's say if it's active, we still have to multiply this value to the negative sign, right? Okay, so for example, 160 times negative 10, that should be negative 1600. So negative times the negative right here, because it's an active element, then that's gonna be positive, right? 1600. Okay, next one, negative 100 times 20, that's negative 2000 times, because it's an active element, then times negative, right? So negative 2000 times negative, that's positive 2000. Okay, next one is passive. So 60 times 6, that's positive times positive, is still positive right here, plus 360. Okay, next one is letter D, 800 times 50, this is 40,000. So this is positive, but it's active right here, so negative 40,000. Okay, next one is 800 times negative 20 times negative, that's gonna be positive 16,000. Okay, and what else? Negative 700 times 14 times negative, that's positive, what's this? 900. 9,800. And for element G, this is 640 times 16, that's times positive, so this is positive 10,240. Right, so now we are going to specify the actual type of element. So since this is positive, then that means that this element should be passive, right? So this one will also be passive, and this one will be active, passive, right? So that's just the actual. So you see that the passive sign convention is just an arbitrary assumption that we use initially in our computations, but later on we can find, or based on that we can actually find the actual type of element. Okay, so to check, so if we sum all this and we compare it right here, we can see that this is actually 40,000 and this is also 40,000. So you can see that the power delivered is equal to the power absorbed. And so therefore it satisfies the conservation of energy. Therefore it satisfies the conservation of energy. Conservation of energy principle. Alright, so next we'll do another sample problem. Okay, so right here it says the numerical values for the currents and voltages in the circuit in figure are given in table. Find the total power developed in the circuit. So the same mechanics that we'll be doing in the last sample problem. And so here's our circuit. We have the elements A, B, C, D, E, and F, and we have this this polarity and the direction of the current. Okay, and we also have this magnitude tabulated already. So now let's do the computation. Right, so first one, let's specify the type of element based on the passive sign convention. So for A, this current enters the positive terminal, and therefore this is a passive element. Right, so if it's passive, then it should be plus. And for B, it enters this one enters the positive terminal, and therefore it's also passive. So this is plus. And what else? For letter C, it enters on the negative, so this is active element, this is minus, and for letter D, enters this current enters the negative terminal, and that's active. So active, and this is negative. Right, and for letter E, it enters the positive terminal. This is passive. And for letter F, lastly, it enters the negative terminal, so this is active. Alright, so negative. Okay, so now let's do the computation. P is equal to VI, so voltage times the current. This is negative times positive, so it will be negative. And if you do the computation, what you get is this, negative 7,038. Right, for element B, negative times positive, so it will be negative 6,750. Right, and for letter C, this is negative times negative, it will become positive, and if you do the math, this is and if you continue, what you'll get right here is 2,400 and 2,352, and plus 8,928. Alright, 8,928. Right, so the actual type of element, so this will be active, and this one is passive, and passive. Right, so the total power produced in the circuit is 13,788, and they are just the same. Right, so total developed in the circuit, so this is equal, the total power developed in the circuit is 88. Alright, so watts. Okay, so basically that's just all that we're going to do for now. Okay, now we'll discuss the Kirchhoffs laws. Right, so in any subject, whether let's say fluid mechanics or thermodynamics, there is a fundamental principle that governs the subject. Like, for example, in mechanics, we have the conservation of mass and the conservation of energy. So it's just typical in any classical subjects. Right, so for this subject, I mean, this electrical phenomena, we have this fundamental principle, the so-called Kirchhoffs laws. Right, so laws because it has two laws. So one law, or the first law, is based on the conservation of charge, or the KCL, and the other law is based on the conservation of energy, or KVL. Kirchhoffs current laws and Kirchhoffs voltage laws. So as you can see here that it's based on our fundamental quantity, the charge, so meaning the charge is conserved, and for the energy, also energy is conserved. So for our first law, Kirchhoffs current law, it says that the algebraic sum of currents entering a node or closed boundary is 0. So in illustration, if this is our electric circuit right here, and we know that this is already a node, this one could be a node, or if we shrink that down depending upon how we see it. Right, so if this is a node, it's a connection point between two or more elements, then that means that the current entering a node, so let's say we have this current in this direction, the current going out in this direction. So of course this is just arbitrarily assigned for now, so the algebraic sum would be equal to 0. Right, so what that means is that the direction of the current actually matters. So it has a sign. So let's say we have this I1 is positive, right? So positive I1, and all that leaves the node would be negative. So negative I2 minus negative I3 is equal to 0. Right? So that's just uh, the basic mathematical expression for this, or the summation of the charges. Sorry, the summation of I is equal to 0. So if we transpose this to the right hand side, we can also get an equivalent expression, which means or which can be stated as this I1 plus I sub 2. Right? So you see this. So I1, and on the right hand side are the I2 and should be I3. So meaning that the sum of currents entering a node is equal to sum of currents leaving a node. So this is an equivalent expression for this Kirchhoffs current law, right? So this KCL talks about a node, or the currents entering a node and leaving a node. It just says that the summation is just 0 because charge is conserved. And if we write this or rewrite this, we can have an alternative expression equivalently the same, something like this. So the sum of the currents entering a node is equal to the sum of the currents leaving the node. Okay, so next one is the Kirchhoffs voltage law, or the KVL, which states that I think I forgot to write it here, but it's the sum of let me rewrite it. The algebraic sum of all voltages around a closed path or loop is 0. Right, so here's the statement of the Kirchhoffs voltage laws. The algebraic sum of all voltages around a closed path or loop is 0. Okay, so if here's our electric circuit, and if we zoom this in, then recall that our definition for a loop is that if we start from this point, then if we trace the path, a closed path, we go back at the same point. Right, so therefore this would be one loop, right? So we have, in this loop we have this active source, and we also have this passive element, right? And it just says that the summation of the voltages is just equal to 0. So therefore, if let's say we'll write this is Vs, our voltage source, and this is our V element, let's say a resistor, and we'll write Vr. So if this is positive, or let's say this is negative, then this one is positive, right? So let's just write negative Vs because it enters this negative terminal. Okay, so plus, if we trace it here, we have plus Vr is just equal to 0, right? So that's the mathematical expression. But if we rewrite this again, if we transpose this to the other side, what we get is Vs equal to Vr, which just simply means that the sum. So let's say in that loop we have multiple sources. So sum of the voltage rise is equal to the sum of the voltage drops. And so so that's the equivalent expression. Right, so this will become appreciated if, let's say, we have this source and we have this element right here, and then we have another voltage source and we have another element right here. So let's say here's our loop. So let's say here's our loop. So here's our direction of current, and let's write this is VS1, and this is VS2, and let's say this is VR1 and VR2. Right, so if we enter right here negative, then we go at positive. This is a voltage rise, and these positive elements will be voltage drops. So this will be plus, and this will be minus, plus and minus. Right, so if we write the expression, that's gonna be starting from this, so negative VS1, right? So starting from this, and then plus VR1, right, and minus VS2, okay, plus VR2. Right, so this is a voltage drop is equal to 0. So the summation of voltages along a loop is 0. Right, so if we rewrite this, let's say if we all the supply side or all the negative side will be on one side of the equation. That's just, if we transfer it to the right side, that's going to be VS1 plus VS2 is equal to VR1 plus VR2. So which means that the sum of the voltage rise is equal to the sum of the voltage drops. Right, so that's the Kirchhoffs laws. So again, if we review this, any subject is based on a fundamental principle, and for our electrical phenomena, Kirchhoffs laws is one of the fundamental principles, which is based on the conservation of charge and the conservation of energy. So for KCL, that's the conservation of charge, Kirchhoffs current law applies to a node, whereas for Kirchhoffs voltage law applies to a loop. Okay, so I think that's all for this week topic, and in the next video we'll be starting our next week topic, or topic number 2, which is all about resistors. Okay, so we'll do computations regarding resistors or resistive or simple resistive circuits. Alright, so see you in the next lecture.